Let's start. So, in the last class, we laid the groundwork of using a voltage control current source to control the output voltage of some resistor divider, regardless of whatever the load connected to it, right? So essentially, what we said was that you can probably realize a contraption like a voltage source using a voltage control current source, and to do that we must use negative feedback, because if you just keep a current source as is, a current source by definition has a infinite output impedance, but a voltage source by definition has a zero output impedance. But if you have to use a current source in order to realize a voltage source, you'll have to do some negative feedback around it, wrap some negative feedback around it, simply because otherwise there is no way for the output to know, or otherwise, I mean, there's no way for some other part of the circuit to know that something has changed at the output, right? So essentially, the whole idea was the premise of using this resistor divider with variable current load. It was not working simply because the information that some load current was changing was not getting transferred, and that transference can only happen if you have some way of implementing a negative feedback. Okay, so these are all very heuristic way of hand-waving way of introducing a topic, but from now on, starting from today's class, we'll delve a bit more deep into what I actually mean by this negative feedback and transferring a current source into voltage source and all those things, right? Okay, any questions before we start? Okay, so
we had one doubt regarding the assignment. Right now, ask that.
I'll have another session for that later on, right? But anyway, if you have any doubt, you just email it to me. If it's a common doubt, I'll respond to the class anyway. Okay. So essentially, what we are saying is, let's say we have a load or generic R, okay, and this load can vary. This load can vary. However, I want this voltage on this across this resistance to be constant, right? Or rather, I want this voltage to be independent of R. Okay, that's the definition of classic definition of a voltage source. Now, when I say it needs to be independent of R, then it needs to be dependent on something, right? I mean, otherwise, what is V0? It can as well be ground. We don't want ground here, but so what we will essentially say is that we want V0 to be equal to, or rather proportional to, some other voltage, Vi, right? And this Vi is known to us. Okay, so this Vi can be as simple as a resistor divider output voltage. Or it can be some very weak signal coming from the atmosphere, right? It can be constant, it can be variable, whatever it can be, but it is. I mean, we would like to have this V0, which is proportional to this Vi. Okay. Now, this proportionally constant can be more than 1, can be less than 1, can be equal to 1. For the time being, we'll realize something, or we'll at least address something where this proportionality constant is equal to 1, right? So for this example, we will try to realize V0 equal to Vi. Okay, so which means we have a Vi somewhere. So let me. So let's say I have a Vi somewhere. Okay, so now, I mean, with that, with the argument that we also had in the previous lecture. So you go to the lab and you want to realize something V naught, which is equal to Vi, and you essentially have a voltage controlled current source, right? So that's what we want to realize, all these things with the transistor. We have a voltage controlled current source. So, and we know that this current source is driving current, which is proportional to some difference of two voltages, right? So that's the definition of our transistor. What is the definition of the transistor? So this is a generic two-port equivalent that we saw that will help us to get gain. So if this is terminal 1, 1 dash, this is terminal 2, 2 dash, then we want effectively this to be the model of our ideal amplifier. But in case of a transistor, it's slightly different in the sense that one difference is that you don't have 4 terminals. These 1 dash and 2 dash terminals are shorted because our transistor is a 3-terminal device. And also we saw that there is a bit more realistic approximation of a transistor is that we have some Y22 also. But we'll neglect this Y22 for the time being. But we will stick to this 3-terminal picture simply because that is what we are dealing with. Okay. Okay. So now I go to the lab. I have this stuff with me, and I want to make V0 equal to Vi. So what will I do? I will essentially change Vi and observe V0. Right? That's the best. I mean, I'll connect it up in some way and I will change Vi and observe V0. And if, for example, let's say V0 is less than Vi. Okay. If V0 is less than Vi, what would you like to do? No, Vi is independent source, right? You don't have, I mean, Vi is coming from somewhere else. That's not a part of the circuit. Resistance is variable.
So we will have more drop if we make the resistance.
Yeah, no. What? Okay, so resistance is also not in your control, right? So what is in your control? It's stuff. You have to make something here which is in your control, right? So you can imagine that you have a voltage source. Input is a reference Vi, and output is V naught, and you can connect whatever you want to V naught. I mean, as a designer, you know a range of R, but you don't know precisely what R is, and that is not in your control. Okay. So what I'm saying is, what are the ways of increasing V naught? You have to increase V naught, right? If you observe that V naught is less than Vi, ultimately you have to increase V naught. And how do you increase any voltage? We don't yet have an amplifier. Yeah, you push in current into a resistor, it increases the voltage, right? So I have to push in some current. I have to push in some current here. But what is the property of this current that you want? Can it be an independent current source? And it should be dependent on what? Right. And so if this current has to be dependent on Vi, so firstly, I have to change the symbol and make it a dependent current source. Now, is it only dependent on Vi? Should it be only dependent on Vi? Note that what was the argument? The argument was if V0 is less than Vi, I need to push in current. So this current source is not only dependent on Vi, right? So it's dependent on what? It essentially is dependent on the difference between Vi and V naught, right? So this current source should be proportional to Vi minus V naught. And if Vi is equal to V naught, this current source will essentially shut off, right? It's not acting anymore. And because we don't want it to act anymore, because I've achieved my goal, Vi has become equal to V naught. But if Vi is less than V naught, I want this current source to keep pushing and pull the node voltage V naught out. So essentially what this is doing, this is trying to neutralize the difference between Vi and V naught by observing the difference first. Okay, so formalizing it.
So when Vi is not in that time, who is driving the arms?
Okay, we'll come to that. So if this is Vi, you want this to be proportional to Vi minus V naught. And can we do it with this model? We can, right? Because ultimately we want this to be proportional to, and this proportionality constant can be Y21, Vi minus V naught, and this is this V naught terminal, and this is Vi terminal. Okay, so this becomes my small signal model of my transistor that is driving a resistor. Okay, now coming to his question that when Vi is equal to V naught, who is driving R? Now note that this is an incremental picture that we are looking at. If you really want to get the total picture, that obviously, I mean, if the current is 0, voltage across R is 0, right? So if you have to take the total picture, you'll have to superimpose a biasing picture on top of this. We haven't got to biasing picture as of now. When we get there, you'll see. Okay, but if you argue incrementally, you will see that there is a certain condition. That is the next thing that we'll do. Under what condition Vi will be exactly equal to V naught? That is a topic for, next discussion that will start in a couple of minutes. But even before going there, the moot reason I am emphasizing this is to show you how you synthesize a circuit. Okay, you start off with first principle logic, and you try to develop, try to connect up what you have in such a way that what you want makes sense. Okay, so what did we do here? We essentially said that we want a voltage source. What is the premise of a voltage source? Output should be proportional to the input. And then we said that, okay, let's start off with a proportionality factor of 1. So then we said, okay, so V naught has to be equal to Vi. If that needs to be done, then first we need to figure out how to establish electronically whether V naught is equal to Vi, more than Vi, or less than Vi. And how do we establish that electronically? We take a difference, we take a voltage difference. So we take a voltage difference and then we push in a current which makes sense to drive the output in the direction of choice, right? For example, if I just had connected in the other way, instead of this current source being proportional to Vi minus V naught, had I connected it in the form of Y21 times V naught minus Vi, would it have worked? Why not? Right, so sense of the feedback is the other way around then. Okay, so vital thing to note is identify the sense of the feedback. And how do you identify the sense of feedback? You have to identify the sense of feedback by first manufacturing a difference voltage. In this case, we have manufactured a difference voltage, or what we call, with the difference voltage that we call, that is Vi minus V naught, or V naught minus Vi, whatever it might be, we call it an error voltage. Why do we call it an error voltage? Because if Vi minus V naught is not equal to 0, then we have not yet achieved what we wanted. Right? So the difference between Vi and V naught is essentially the error. If everything is proper and everything is working perfectly, then the error should go to 0. If it's not working properly, then there will be a residual Vi minus V naught. That is the error, right? So first thing is identify the sense of feedback. Second thing is manufacture an error voltage. So in this example, our error voltage, let me call it VE, is Vi minus V naught, right? So this is in this example. And then what we do? Then we drive the output with something that is proportional to the error voltage, right? So next thing is drive the output with a source dependent on P. Okay, So this essentially is a 3-step process of generating anything using negative feedback. Now, this is a very top level process. There are more nuances to it. We'll get to those as we move ahead in the course. But overall, this is what we do even in our mind, right? So for example, if I ask you, if somebody from here, I ask him to go out of, give a direction to one of his friends to go out in certain way that you don't hit anything, but go out of this room, right? So one way to say that is that he will say that, okay, stand up, go to the left, go in front, 5 steps in front, then 20 steps on the right, and so on. And you will find a door, right? So that is one definite way of advising a direction, right? But the issue is if you're slightly wrong and the folk he's advising is not seeing anything, then there is a chance of hitting something and falling over and causing mishap, right? So this is an open loop way of advising something, right? You told something and the guy followed. And something is wrong in your advice, you're gone. But another way of advising would be take one step, touch around and see whether something is in front of you you can still move ahead or not. Take another step, see if you can move ahead or not. After you come maybe 4 or 5 steps, you will see that you face a blockage. Then you move around, you observe your surroundings. Then you will see that something is open on the right, go that direction, and you will keep on doing that. You will eventually reach your goal. So this is a negative feedback way of observation, right? You always observe your surroundings with a goal of where you want to reach and take corrective action, right? If you cannot go left, observe and see which side you go, which side is empty, you go that side. So this is this is a continuous way of sensing your environment and taking corrective action. So this is what this circuit is also doing. It is always sensing the difference between Vi and V0, figuring out what the error voltage is, and then taking an action. And it will keep on taking an action unless Vi is equal to V0 ideally. Okay, does it make sense? Any questions? Okay, so now we have been dealing with Y21, Y22. These are generic parameters, but in case of a transistor, we call Y21 to be transconductance. So we call Y21 to be GM. So for MOSFET, Y21 is GM, and Y22 we call it as GDS, right? Or this is also 1 over RDS. DS is essentially drain to source. So this is some terminology will follow from here on in. So let me redraw this contraption. By the way, here I didn't say what should be, this we know is a drain, this we know is a source, this we know is a gate. So what should I connect this drain to? Incremental, right? We don't have any VDD or anything. It should be an incremental ground because ultimately this is a current source and we are not doing anything on the drain side. And obviously you don't want very high, you don't want any high impedance there because what will you do with a high impedance on the drain when you are not even observing the drain, right? So we can as well incrementally short it, right? Okay, so this is my V0. So find out what is V0 over Vi exactly. Find out and let me know. Yes, what is it? GM by G plus GL. GM plus G, right? Okay. So under what condition your V0 will be approximately equal to Vi? G is not in your control, but GM is in your control. So what will you do as a designer? Right. So you want, correct. So you would want GM. So if GM is much greater than G, then V0 tends to, yeah. Okay. So now the question is, math checks out, but Does it make sense? Right? So this is always you'll have to go back to see, go back and ask yourself whether it makes this result makes sense intuitively. Now, why does it make sense? Because the question that he asked, that when will Vi, what happens if Vi minus V0 goes to 0? Who is driving the output? Right? So when, under what condition Vi minus V0 will become 0? Gm tends to infinity, right? When Gm tends to infinity, it is possible to have 0 input, but still a finite output, right? So essentially, this is a recurring theme that you will see, that if you, I'm sure all of you are familiar with ideal op-amp circuits. When you use ideal op-amps, what you see, you say that, okay, I have infinite gain, then I can have virtual ground. You have virtual ground means input of the op-amp is essentially 0, but still you have an output, and the output is proportional to whatever you want. You still get gain, right? So this is a classic example of that. If Gm goes to infinity, the difference between Vi and Vs, right? So this is Ve, this will tend to 0 if Gm tends to infinity. So this will become virtual short incrementally, right? So if you have infinite Gm, in this case, it looks like you get a virtual short. Or if I have to be more precise, what I need to do is I have to ensure that Gm over G goes to infinity, right? So it's a relationship between Gm and G, not Gm independently, right? So Gm has to be much greater than G, or in other words, Gm over G or Gm times R has to go to infinity. It is only under that condition I will get V naught equal to Vi. Now nothing can go to infinity, right? Which means that you will get some error. You will always get some error between V naught over Vi. However, depending upon whatever application you are interested in, you might choose to live with that error, or you might choose to reduce that error by further increasing this factor of Gm over G or Gm times R. Okay, does that make sense? Now, what happens if what happens if I connect a variable, another variable load here? Let's say I call it GL. Does it change anything? To the argument, does it change anything? No, because GL comes in parallel to G. So essentially, I'll have to recalibrate my G and C, right? So if I give you a range of GL, right? If I give you a range of GL, which value of GL you will take to figure out what GM you want? So smaller value of GL or larger value of GL? Larger value of GL, right? Because ultimately, when you have output, right from this expression, you see that you would want Gm to be much greater than G, and if G has a range, obviously the maximum value of G is the one that you should take. Okay, fine. So this looks like a output which is independent. We can fairly realize an output which is independent of which is proportional to V naught. Vi is proportional. V naught is proportional to Vi. And also, the other important thing to note here is that it is independent of Gm. Largely, it is independent of Gm, right? You might say, I can see Gm by Gm plus G, right? But what you need to understand here is that what is the error between what I want and what I'm getting? So what I want is V naught to be equal to Vi, and what I'm getting is this. So what is the final error that I'm getting? What is the final VE? Eventual VE, right? So VE, this is final. When everything is working, settling, no issues. So what is the final VE? It's not 0, right? It's 0 only when Gm by G tends to infinity. When Gm by G is not infinity, what is the VE?
G upon Gm plus G.
G upon Gm plus G, right? So this I can also write as 1 by 1 plus GMR. And if we target GMR to be very large, So this is approximately equal to 1 over GMR. Now note that this error voltage will keep on reducing as you increase the product of GM times R. And that also makes sense because as we keep on increasing this factor of GM times R, V naught tends to go towards VI. Now, the important thing to note here is that your V naught is largely independent of VI, but there is a dependence. There is a dependence of one. I mean, the error voltage is dependent on 1 over GMR. But the error, as long as you can make that error voltage very small, let's say less than 1% or less than 0.1%, whatever be the might that requirement might be, then you can say that for all practical purposes, V naught is independent of GM. Right? So if my yes.
V is the error voltage,
right?
So it's the dimensionless, but still.
Okay, sorry. Yeah, thank you. So this is VI. Thank you for pointing it out. Okay, so what I'm trying to get at here is that ultimately, let's say your application demands that your V naught should track VI, that is V naught minus VI, should be less than 1% error, right? If I say that the error should be less than 1%, that is V naught minus VI should be less than VI by 100. So from there, you can figure out what your GMR needs to be. If you know R, from there you can figure out what is GM needs to be. But if you note that this doesn't have two limits. This error need not be precise. It has to be less than some value. As long as you can realize what the less than condition, it doesn't matter if GMR is higher than whatever you need to be, right? So which essentially means that if you can satisfy this across all range of load conditions, then for all practical purposes, V naught is independent of VI. Sorry, VI is independent of GM. Okay, so why is that critical? It is critical because note what is our GM? Our GM is dependent on threshold voltage, dependent on nu, Cox, which are in turn dependent on ambient conditions, temperature, mobility, and so on, which are totally not in your control, right? You have got a device, whatever device you have got with however bad the parameters are, you have to live with that. But small signal parameters that you have derived or extracted from the device, that is GM, GDS, and so on and so forth, these are all dependent on ambient condition variation. So job of a designer is to get those devices and make an overall system which is not dependent on ambient condition. So let me repeat. So if you have been given devices which are largely dependent on ambient conditions. If temperature of the room changes, performance of the device will change. But you want a system which works regardless of the ambient condition variation, which means you will have to use some method that you plan to use those devices, but the system will not be dependent on ambient condition variation. And how can you do that? This is an example where I show you how you can do that. Right? You are still using a transistor, but your output voltage is not dependent on the transistor parameters. Okay, so it's not strictly mathematically true because you see there is a factor of GMR, but for all practical purposes, as long as you can keep this GMR to be large enough, then you can make a system, in this case, a voltage control voltage source, which is largely independent of ambient condition variation. Okay, this is another very important crux of why people use negative feedback. It's in order to stabilize the performance of the device when everything around it changes. Okay. Okay. Now, this is what we saw. I mean, whatever we did is from the transfer function perspective, but a voltage controlled voltage source has two other important properties. One is its input impedance should be high-low. It ideally has to be infinity, and output impedance ideally has to be 0. So obviously in this case, the input impedance is what in this model? It's infinite. I mean, our transistor model that we have taken in this case is infinite, but what is the output impedance? Now, let's say I ignore GL and let's say I look in and find out impedance. What will be the impedance?
1 by GM plus G.
GM plus G, right? Not 1 by G.
Sorry, GM plus G.
Rest of the class, do you agree? Okay, so essentially, V naught, Vi. How do you figure out what is the impedance of any node? First thing, you desensitize any independent input. In case of a voltage source, this is grounded. Then you look at a certain node and then you apply a test voltage or a test current and see what is the eventual current or voltage. So in this case, if we apply a test voltage, we test, this current will be GM times Vi, which is 0 minus V test. This current will be V test times G. So this effectively means that you have a current that is going up, which is GM times V test, which means the current that we are pulling in from the source, that is I test, is GM plus G times V test, which effectively means that your R out is 1 over GM plus G. Now, obviously, I mean, when you are using real devices, you will never get 0. But as long as you can make this GM plus G to be much larger than something. Now, what is that something? That something has to be the load that you are eventually driving, right? So you will have some load here. So you will have some load here. And whatever you found out, this R out is essentially the Thevenin equivalent output impedance, output resistance. So as long as this R out is much lesser or much larger than RL, has to be less, right? As long as this R out has to be much lesser than RL, or this effective G out is much greater than GL, then the condition of voltage source is satisfied. You have output resistance to be equal to, I mean, not 0, but output resistance, output impedance is much smaller than the load that it is driving. Okay, and that also comes out from this requirement, right? So if you do this calculation using GL, you will see that you would want what? You will have plus GL term here, right? You will have some plus GL term here, and you would want, still you want this ratio to be independent of G, GL, GM and all those things, which means you would want GM plus G to be much greater than, or rather GM in this case to be much greater than GL, and that is what exactly that you see from this expression. Okay, any question? No? Okay. Fine. So to quickly recap, what were we seeing? We are trying to realize a voltage source or control voltage source from a controlled current source using negative feedback. Then we saw what is the standard method of going about doing it. You observe the output and try to feed in that information at the input. So in order to do that, you'll have to figure out what is the error voltage. What is then from, depending on the error voltage, you have to drive the output in the correct sense of feedback, and then hope that everything falls in place. But how do you figure out whether everything falls in place? You do an analysis and figure out the constraint, right? Because nothing is infinity. You'll have to figure out what is the constraint under which your hope is actually turns into action. So that limit is essentially what we are looking for. Okay. So there is a synthesis part to it. This is an analysis part to it. Okay. So this is what we did. I mean, this is the voltage control voltage source. Let's also do the same thing for voltage control current source, right? So let's see voltage control current source. Now you might say that we already have a transistor which is a voltage control current source. Why do we bother? Right? Now note that the transistor, the proportionality constant, if transistor is used as a voltage control current source, the proportionality constant is Gm. Now again, Gm is dependent on ambient conditions. So if we want to generate a voltage control current source, which is largely independent of ambient condition, then we cannot have the proportionality constant to be equal to Gm. Okay, so if we assume that in this case, I mean, let's assume that we have a resistor. Again, we have a resistor R, which one might say is also dependent on ambient condition, but let's assume it's not. Or as it turns out, the variation of resistance with temperature is much smaller than with respect to Gm. So that is not a part of this course, but let's assume that we have a resistor which doesn't change with ambient condition. So in that case, what we are looking for an I out which is proportional to V in, right? And the proportionality constant is some conductance, okay? And which is independent of Gm, right? So that's the whole purpose of doing all these things. Okay, so I have a V in and I have a R or G, right? So this can be our proportionality constant if we play our cards right. Okay. So I have, I mean, obviously, if you have I out, you have a port from which you are drawing I out. So let's say you have I out. This is a port. Okay. So now, taking cue from whatever we did in the previous example, what is the first thing that you need to do? Identify what? Identify the sense of feedback, right? So see, identifying the sense of feedback and figuring out what is the error voltage go hand in hand, right? So sometimes you have to identify, sometimes it's quite apparent what is the sense of feedback. Sometimes you have to figure out what is the error voltage and then go, then figure out what is the sense of feedback, okay? So let's do the other way around. Let's figure out what is the error voltage. So if I have an I out and I have to compare it with V in, I have to figure out what is the error voltage. Now, obviously, I cannot compare a current with a voltage. They are not of the same dimension. Okay. So easiest thing to do is to convert this current into a voltage and then compare. So what should I do? Pass it through R, right? So I out pass through R, somehow pass through R. So let's assume I have passed I out through R and I have generated this voltage. This voltage is I out times R. So now what should I do? Yeah, but what is the first thing that we should do? We should figure out an error voltage. What is the error voltage? V in minus I out R. And I want this error voltage to behave in such a way that if let's say I out is smaller than what I want, right? So I out is smaller than what I want. I need help from V in to push in more current. Okay. So which essentially means that I again need a voltage controlled current source, which is proportional to V in minus I out times R, right? So this is nothing but again our transistor. But note that now I am looking from the drain of the transistor. Well, we are not really looking from the source side of the transistor. So this was the source, this is drain, scale. So the same contraption that we had that behaved like a voltage control voltage source in the earlier example can behave as a voltage control current source. We haven't yet done the analysis, but if the argument is correct, the same contraption can behave as a voltage control current source if we look from the drain terminal of the device. Okay, and that shouldn't be surprising because we know that looking in from the drain of a the output impedance of a transistor is ideally is infinity, right? And that is something that we also expect from a current source. Okay, so and we saw in the last example, if you look into the source of a transistor, right, source of this transistor, then output impedance can be quite low. It's of the order of 1/Gm. So essentially, I mean, it makes sense that looking into the drain of the transistor, we are getting a current source. Okay, so now tell me what is I out with respect to V in, exact analysis. I out shouldn't change. It was the same thing that we had in the previous example, right? So what will it be? GM by times V in. Okay. So under what condition that is independent of GM? This proportionally constant? If GMR is much greater than 1, then I out is approximately equal to V in over R. Right? So you get a voltage controlled current source which is largely independent of the small signal parameters of your transistor. Okay. So note that this V in, I out, these are all small signal parameters. These are all incremental we are talking about. Okay. So regardless of frequency, it can be DC, it can be infinity. It doesn't really matter because we haven't really taken capacitor and all those things into account. So as far as this model is concerned, it works across all frequencies. Okay. So now proportionality constant checks out. The other two things that we need to check out is input impedance, output impedance. Clearly input impedance is infinity. What is the output impedance? Let me redraw. Inputs get shorted and you are applying a test voltage. And figuring out what this current will be. Now, if we apply a test voltage in this contraption, right? So this is GM0 minus V0. If we apply this test voltage in this contraption, what will be I test? So if I simplify it and just say that I have one only transistor, nothing else, here it's grounded, right? Input is grounded, this R is 0. And I find out output impedance. What will this output impedance be? Y22 will be 0, R out will be infinite, right? So it doesn't matter if I put anything here, right? Why doesn't it matter? Because my current equation, if you think about it, or current, I mean, when I am not considering the GDS or Y22, right? What I am essentially saying is that IDVD characteristic is flat, right, in the saturation region, which means it's a current source, which means its output impedance is infinite anyway. Okay, so it really doesn't matter what you connect at the other end of the current source. Shouldn't matter, right? If I connect anything here, or for the matter, if I connect anything here, should it matter? It's a current source. Wherever you look, everything is in series with the current source. So whenever you look from any terminal, you should get infinite output impedance, right? But obviously, I mean, we made an assumption here, and the assumption is that Y22 is 0 or GDS is 0, which is strictly not true. So you'll have to be more realistic in this case. So let me put this GDS back, or RDS, or whatever you wanted to call it. Now you tell me what will be the V test. And this, I think, was a part of the assignment also. You can directly tell as is. And how will you go about? Yeah, you're right. So how will you go about doing that? The way at least I prefer doing that is, if this is I test. So I know that this is a box. Whatever goes inside the box has to come out. So this has to be I test also. So if this is I test, this voltage has to be I test times R, which means this current, which is GM times 0 minus I test times R, which means it's going the other way around. This side is GM times I test times R. Then you solve for KCL and you get, right? So what is the final thing? So what is R out? Somebody told RDS plus R, GM RDS times R. So when RDS was infinity, it was going to infinity because you clearly see you have one term here and another term here, right? Which is proportional to RDS. But which one is the dominant factor here among the three addition terms? GM RDS times R, simply because you don't want to use a transistor which is not in saturation in these cases. So when you are using your transistor in saturation, then clearly GM times RDS has to be much greater than 1, which means that this is approximately equal to GM times RDS times R. Okay, and this is true. This is true as long as your GM RDS is much greater than 1. Okay, make sense? Yes.
Sir, when you just say when the IDVDS for this flat, in that case the resistance is infinite. But sir, from the DC point of view, we say it has some finite current and some finite voltage according. So and you again said that there's a small signal current is applicable for both DC as well as any frequency. So how do you say?
Good question. So let me throw it to the class also. What he is saying is, I mean, when you bias your, if you observe the IDVD characteristics of a MOSFET, you get something like this. Okay. So, and if it's if it's an ideal, it is flat, slope 0 in the saturation region, then RDS tends to infinity. Okay. And what was the follow-up question?
So if I apply a DC voltage,
right.
That is
okay. So then I also said that this whatever I am saying is applicable for all frequencies, even for DC. But it looks like at DC I have some ID Q and VDQ, right? So I mean, what is wrong? What am I missing? Okay. So we did say we are talking about incremental inputs. When I say incremental input, that doesn't mean that I am discarding DC. What does incremental DC mean? Let's say I have certain bias point and I have increased the bias point by bias voltage by some delta V, and I observe for after that for infinite time. That is an incremental DC. I'm starting my observation after everything has settled, right? So which means that, let's say initially I was somewhere here, right? Then I slightly increased my VDS, and I moved here. My current hasn't changed. Incrementally, my current hasn't changed. So it's an incremental infinite output impedance, not absolute. Okay.
So if I apply a DC voltage, in that case, I will find like resistance of this VDQ by IDQ. Right?
Yeah. So I mean, for example, if I simply, let's say I have a current source, independent current source, let's say I0, and I observe, for some reason, I observed a voltage of 2 volt across it. Does that mean my R out is 2 by I0? It doesn't mean, right? Because one might argue that V by I is my Ohm's law, right? V by I is resistance. Yeah, but I can say that this is this V by I resistance is true if everything is linear, right? But here we are talking about it's linear in an incremental sense, right? Not in the absolute sense.
like this is a flat. In that case, you can say it's a sort of linear.
Actually, then you have to go back to a very basic definition of linearity, right? So if you just say that y equal to mx plus c, if c is non-zero, will superposition hold?
No, sir, no.
Right?
Zero
Right. Yeah. So it boils down to that, right? So yeah. Okay. There was something else I was trying to point out. Okay, so if all these things are satisfied, we saw that this I out is equal to V in over R. Okay, so can we make these? Can we make these approximations without doing all these analysis? Okay, so let's forget about RDS for the time being. Let's assume RDS equal to infinity. Okay, we are satisfied that output impedance is whatever we want. As long as we are satisfied, then we can discard that and reduce our analytical burden, right? So let's assume RDS equal to infinity, which means get rid of RDS. Now, under what condition your output will be V in over R, or the current will be V in over R? Yeah, so under what condition? GMR has to be much greater than 1, right? So this is the same thing that we did in the voltage control voltage source example. So GMR has to be much greater than 1. And why does it make sense? It makes sense because if GMR is much greater than 1, what is the source voltage? Is approximately equal to what? If I observe at the source, what do I get? V in. If this is V in, the voltage, the current through this is V in over R approximately, and that eventually comes out. Okay. So now you have to be, I mean, often I see sometimes students make this mistake, but you should be careful with this, is that which approximation to take when. So this approximation Vs is approximately equal to V in doesn't mean VE error voltage has gone to 0. Right? So when you are comparing something with 0, you cannot really discard anything. When you are comparing something with a large quantity, you can discard a small quantity. Right? So your error voltage will only go to 0 if you have infinite GMR. Right? But that doesn't mean that you can never approximate the source voltage to be equal to V in. You can still do that because as long as the source voltage, I mean, V in is much higher than 0, for example. Right? So in that case, obviously you can do that approximation. Okay, so be careful when you want to do these approximations, because the trap is if you don't do the approximation, you get lost in algebra and you have only so much amount of time. So you'll have to be careful. I mean, what differentiates a good designer from not so good one is one knows which approximation to take when. Okay. Any questions? Okay, so we have covered voltage controlled voltage source, voltage controlled current source. Now we have basically 2 cross 2, right? We can have current controlled voltage source and current controlled current source. So let's do the current controlled current source. By the way, I'm sure all of you have seen all these contraptions before. I'm just trying to synthesize it from the perspective of, I mean, somebody is starting from scratch. How would you go about doing this? The reason I'm doing this is not because these are the only types of solutions possible. The reason I'm doing this is because this is the design thinking, right? So if you come up with a with a problem or a question or something where you are asked to design something, you should be able to use these reasonings to come up with a solution. Okay. Okay. Current control, current source. So when I say current control, which means by definition you have an input current. You have a given independent input current source. So you have an input current source I in. And output also is supposed to be a current source, which means you are taking some current out. Okay. So now you will have to compare two current sources essentially. Now I out we know has to be a dependent current source, because ultimately we are using a transistor, which means I'll have to compare two currents. And how do you compare two current sources? Yes, KCL, but in case of circuits, how do you connect two current sources to figure out whether one current is higher than the other or smaller than the other? Is there a way to do that? Okay, right. So if let's say I have two current sources, let's say I1 and I2, right? And if I observe this voltage, this intersection voltage, if this intersection voltage is going up, then I know that I1 is more than I2. So the intersection voltage is going down, I know the I2 is less than I1. And this is exactly what we don't want to do, as we discussed in the last lecture, right? Because as we don't want to do with two independent sources. If they're talking to each other and adjusting their values, their strengths, it's fine, it's acceptable. But you don't want them to be working independently. Okay. Okay, so now we know that we have a control source. We connect this control source up. And this is, let's say, I out. Then we'll observe, right? What should we observe? We should observe this voltage. It's a Vx. So if Vx goes up, so essentially we'll have to figure out what is the error voltage, right? My transistor is essentially a voltage control current source. We are doing everything with the transistor. So we have to figure out what is the error voltage. So if Vx goes up, what am I inferring? The stuff on the top is stronger, right? And the Vx goes down, I know that I in is stronger. So if Vx goes down, I know what I want this if Vx decreases, we want the control source to increase its strength. Okay. So then what is the error voltage? We don't have any V in, right? Vx itself is error voltage, right? I don't have any V in. At least, what I do with V in is a different thing. We have a terminal, we have a gate terminal, but we don't have a V in. But do we require a V in? We don't, because ultimately Vx itself is giving the information that I want. If Vx is going down, I know that this stuff has to go up, right? Go up, value has to go up, and Vx is going up. The value of this proportionality, whatever factor, has to go down. So Vx is good enough, right? So all we have to do is to generate a current source here, Gm times. Not really, right? Because think about it. If Vx goes down, I need this current source to increase in strength. Opposite. So sense of the feedback, right? It's an opposite direction. So if I just say it to be Vx, right? Let's say assume that you figured out, you did one iteration and in your logic, you missed something and you put Gm times Vx. What happens? If Vx goes down, then Gm Vx also goes down, right? But that's not what you want to do. You want to increase Gm Vx, right? So essentially, incrementally, this should go up. This should be minus Vx. Right? Which means that I don't need the gate. Incrementally, the gate can be grounded. And I simply connect my transistor in this, the small signal model of the transistor in this manner. Make sense? Now, obviously, I out in this case is equal to I in. There's nowhere else for I in to go. Whatever comes into the source terminal has to go out of the drain terminal. What is the, when you have a current control source, what is the expected input impedance of a current control source? Let's say I have a block input, I'm expecting it to be a current. What is the expected input impedance? Pardon? As small as possible, right? Should be close to 0. So in this case, we have a source, which is in. Okay. What is the input impedance? Somebody else? 1 over Gm, right? So, so now if you have an ideal in, I mean, okay, let me take a step back. And I said that the in, we have an in, and in goes into I out. That's true. But as it turns out, you also don't ever have an ideal current source, right? Just like you don't have an ideal voltage source with 0 impedance, you don't have 0 series resistance, you don't have an ideal in with an infinite resistance at its connected in parallel, so which means that you have some RS, right? Where RS is, I mean, has to be high, otherwise it's not a current source. Okay, so now under this condition, right? Under this condition, what do you expect the constraint to be for I out to be approximately equal to I in? Exactly, right? You would want all the current of I in to flow into the source, into I out. You don't want the current to go into RS, right? As you said that R in has to be close to 0. So if everything is fine, if the design is working fine, you want all the I in to flow to the output and nothing to flow into RS, which in another way of saying is the impedance looking into the source of the transistor has to be much lesser than the impedance that you were seeing in parallel connected to the I in, right? So effectively you would want, for this to get satisfied, you would want Gm to be much greater than Gs. Okay. And I leave it up to you to do the math to see whether I out is actually equal to I in if this condition is satisfied. Because now clearly, if you look at this node, there is a current division happening, right? Some current will flow this side, some current will flow this side. So I out can never be equal to I in a true mathematical sense, but approximately is I out equal to I in when this condition is satisfied. And you will see that it actually makes sense, right? And easy way to validate these things is to say, let's put Gm to be equal to infinity. If Gm goes to infinity, then clearly the incremental impedance looking into the source of this device is 0, which means I in has nowhere else to go but into the device, right? So when the incremental, again, I mean, if the incremental impedance is 0, you can see that the error, I mean, transistor error, the only way transistor can sense an error is by looking into its difference between Vg and Vs, right? So this voltage, this VE, it tends to 0 when Gm tends to infinity, right? So again, virtual ground that you see in ideal op-amp case, right? In ideal op-amp case, the comparison terminals are those plus and minus terminals. In a MOSFET, the comparison terminals are the gate and the source terminals. So if you have infinite gain, so as to say, in this case, gain can be anything depending upon how you have connected it up. In case some cases Gm times R. In most cases, you will see Gm times R, but what is that R, what is that Gm is that you have to figure out. But as long as you can get the so-called gain to be infinity, the difference between the comparing terminals will go to 0. Same concept as ideal op-amp. So essentially, if you have to make an ideal op-amp kind of scenario only with a MOSFET, you would want a MOSFET with GM tends to infinity or GM times R something tends to infinity. Then you can use a simple MOSFET as an op-amp also. Okay. But unfortunately, we cannot, because they have its own limitations. You don't get infinite gain. So those are the things that we'll see later. Any questions? Okay, so we're done with CCCS. Before we end, let's do the last one. That is CCVS. Yes.
Looking at the source, the impedance is 1 by GM.
Right.
And it is independent of whatever we connect in the drain side, right?
Good question. So let's say I have some stuff connected here. Gate is incrementally grounded, and I'm looking into the source. I'm finding out what is the out. And I have some load connected on the drain side. So is R out independent of that ZL? Why not? How many of you think R out is independent of ZL? And how many of you think it's not? A lot of no thinkers. Okay, so I mean, okay, so let me ask the folks who raised hands. So why do you think R out is independent of ZL? Okay, right. So this is essentially what? GM times 0 minus, if I apply a V test here, V test. Right? So if I apply a V test here, the current that I'm drawing out on top, if we ignore whatever is connected on the bottom, if I connect the current that I'm drawing out is GM times V test, which means the impedance is GM 1 over GM. It's independent of ZL, right? It's actually independent. So what is your follow-up question?
For the ideal current source,
right?
Which is like not independent current source. You know the internal impedance is infinite.
Right.
But in this case, it's a dependent current source, but the internal impedance is like 1 by GM. So.
No, which terminal are you looking in?
In the source terminal.
But is it a current source when you are looking into the source? So when you have a dependent source, you have to identify what is it dependent on, right? So good question actually. So is it a current source looking from the drain side or looking from the source side? What is happening if I look into the source? I am directly affecting the current of the current source, right? I am changing the voltage and current is changing. So when I change the voltage and current changes, it's definitely not a current source. But if I look into the drain, I change the voltage, nothing happens, because ideally there is nothing connected between drain and source, which is proportional to the voltage, which will cause a current which is proportional to the drain voltage, right? So, but in reality, we have an RDS. So this RDS makes this dependence poorer. I mean, this RDS makes it a poor current source.
I mean, when you are looking towards the drain.
Correct. When you are looking towards the drain now, if you are applying a test voltage here, when you are applying a test voltage from here, now clearly there is a path for this incremental V test to percolate into the source, towards the source, right? So this current will have some proportionality with respect to V test, right? So this becomes, this is not an ideal current source anymore, but under conditions of what GM times RDS to be much greater than 1 and all those things, then you can get a better current source. But if we ignore RDS, clearly it's an ideal current source, because isolation between drain and source is perfect if you ignore RDS. Okay.
So basically the current is coming from the G test and going through this RDS, and that is basically affecting the source voltage, and that's violating the properties of like current source.
Yeah. So essentially, if you moment you are having a voltage, a current which is proportional to V test, right? Proportional to the voltage you have applied across that contraption, it's no longer a ideal current source. And in principle, you will never get an ideal current source. There is never infinite isolation. Yes.
And sir, when we are applying the voltage source in the source terminal, and we are directly affecting the controlling.
Right. Exactly. So this small, the simple transistor can behave both like a voltage source and current source depending upon how you connect it up. Okay. So the question that led to this is the fact that under what condition, I mean, we said that here input impedance looking in towards the top, right? Let me remove this, it will unnecessarily be creating confusion. Is always 1 over GM, right? It's independent of ZL. But if you have RDS, will it be independent of ZL? No, because now if this voltage increases because you have pushed in some current, there will be some reverse current. It can be a reverse current, right? Which means there will be certain limit on RDS for which it will behave as a current source, and beyond that it will not. That was also, I think, one of the questions in the assignment. I mean, not in these words, but I asked you to plot something. Okay. Okay, so we are out of time. We'll stop here. Any questions before we stop? Okay, see you.